Okay, so moving on, let's talk about ANOVAs. So whenever you have more than two conditions, you're going to run an ANOVA. When you only have two conditions, you're going to run it. Right? So this example here, say we're looking at, let's say amount of exercise and lifespan. So you exercise a lot, here's your lifespan. If you didn't exercise a medium amount, here's your lifespan. Um, if you exercise very little, here's your lifespan. So we have three people in three conditions. And again, we measure their lifespan, that sort of variable. So in that example, we're going to run an ANOVA because we're going to want to figure out, first of all, whether there's anything going on there. Let's start with that, and then we'll get into the specifics. So the whole premise behind an ANOVA, which by the way stands for analysis of variance, is that you're taking different sources of variance, you're kind of separating them. Okay. So there's multiple places where scores can vary, and we're going to separate those, and that's going to tell us a great deal about whether there's actually a population difference or not, or whether there's actually an effect or not. Okay. So the main two we're going to be concerned with, there's actually a third one, but these are the two we're mainly concerned with, are between groups variance and within groups variance. And hopefully remember this, but variance is just change, really. So if you have, say, six fives in your sample, whatever this kind of variable is, there's going to be no variance there because all the numbers are equal to the mean, right? If you have 100, 5, 7, 25, there's going to be more variance because the numbers each differ from the mean. Okay. So when it comes to an ANOVA, what we're going to do is we're actually going to be looking at different sources of variance. One is something known as between groups variance, and the other is known as within groups variance. Okay. So between groups variance is differences between the condition means. So the difference between this yellow bar, this orange bar, this red bar, the difference between those and this mean here, the mean of basically every score. We'll get into the calculations next, but just kind of remember that part for now, that how much are the conditions different from the rest. Okay. That's what we mean by condition means, or between groups variance. How much, again, do the condition means vary? On the other hand, we also have within groups variance, meaning how much do individual scores within a condition vary. So, for example, all these people in the high exercise condition, how much do they vary from each other? How much these are just two, but 25 and 27 differ from one another? How much does 13 differ from the other scores in the medium condition? How much scores within the low condition differ from one another? And we're actually going to use these two things, and it's going to tell us something again about whether there's actual population differences, or at least suggest whether there's population differences or not. So just try to solve this for a second, and then I'll give you the answer. Why do you think that there might be between groups variance? Why would, say, condition ones, or the low condition mean, medium condition mean, and the high condition mean, why might those be different? Well, there's two reasons, and this is really the same as we've talked about with t-tests. So they could, of course, differ because, or actually, before I give that away, also, why might there be variance within groups? So why might two people, well, not just two people, but as an example, two people within the same condition, like 25 and 27, why might those be different? about that? Well, between groups variance is a result of two things, just like with t-test, just like with pretty much any stat that I know of. There's between groups variance potentially because of an effect or population differences, and also because of error, because of extraneous variables. Okay, so just looking at this example here, you don't have to worry what these conditions are. You might get 12 in this condition, 4 in this condition, 1.6 in this, and 0.46 in this one, for two reasons, right? One is that this manipulation actually did something, and there's actual population differences there. The other reason is just sampling error, right? Individual differences, extraneous variables, right? So maybe I just happen to grab a bunch of people do well on the memory test and they happen to get sorted into this condition, and people not doing well in this condition, so on and so forth, right? That's what we've talked about, just sampling error. So that's what contributes to between groups variance, both potentially an effect and just extraneous variables, things we can't control, things that are causing differences, but we're not actually manipulating, like say individual differences, how hard do people try, um, how good of a driver are they, whatever it might be. Okay? And we expect that those are going to even out across conditions because we're randomly assigning people. But like we've talked about for a while now, it's random, meaning it could not be perfect. Actually, it won't be perfect. You could still end up, through bad luck, with more high scoring people in one condition than another. Right? So that's between groups variance. Possibly your independent variable, but also error variance, extraneous variables, measurement errors, individual differences, all that stuff. But also possibly your independent variable. Now, on the other hand, within groups, would these be different due to a manipulation? So would this person who got 15, why would they be different from the person who got 8? Would it be due to any manipulation? Well, no, right? Because they're in the same condition. They're getting the same treatment, whatever that is. Okay. So just like in this one, the 25 and the 27 are not going to be different from each other because of treatment differences or independent variables, because they're in the same condition, right? So what that has to reflect then is just error, right? Extraneous variables, measurement error, all that stuff, right? Just going to be error within the same condition. So we'll come back to this, but for now, and we'll go into the calculations more, but for now, the logic behind the ANOVA is it's going to give you something known as an F ratio. Okay. You also have to divide by degrees of freedom, which we'll get to as well. But for now, I just want to show you what this looks like. So an F ratio is going to be dividing, again, including degrees of freedom, which we'll get to, possibly error variance, and also, or error variance for sure, and also possibly variance from our manipulation. And you're going to divide that by the error variance. That's the logic behind an ANOVA. So really what all we're doing here is we're going to divide, again, after dividing by degrees of freedom, between groups variance by within group variance. Okay. So let me say that one more time. Dividing between groups variance by within groups variance. And what do those things reflect? Well, remember we said that between groups variance on the top here is error variance plus possibly variance from our manipulation. On the bottom, we have within groups variance, meaning it's just error. Okay. So thinking about it, just mathematically, if the F is greater than 1, what does that suggest? I just stick in some numbers in here, see what happens. Well, if the F is greater than 1, that must mean that, or at least indicate, I shouldn't say must mean, but indicates that there's something going on, that our manipulation is actually doing something. Because these should cancel out, right? So on the other hand, if our f is equal to 1 or less than 1, that would suggest that we're just dividing error variance by error variance, right? However, the more upwards of 1 that our f gets, we know that, okay, well, these two canceled out, but because it's still greater than 1, that must mean there's also variance from our manipulation, right? Again, one more time, if the f is substantially greater than 1, that would suggest this is not 0. This has to be, something important, because these two are canceling out. So it means that our manipulation likely had an effect. And again, if it comes out equal to 1 or even less than 1 or only slightly above 1, it would suggest that there's nothing here because we're just dividing this by this, which are the same thing, right? So that's the logic behind an ANOVA. We'll return to this, but let's next get into the actual calculations.